Mukti Patodi, can you hear me?
Yes, ma'am.
Thank you. So we were dealing with the dipole moment. Dipole moment we expressed with this cut arrow. Chlorine is more electronegative. The moment is towards that direction. Now let's see in compounds, in compounds having more than one bond. In that, what is the dipole moment? For example, H2O, HOH. Here oxygen is more electronegative. This is a vector quantity. So dipole moment is a vector quantity. So there will be a resultant towards up. So there is a net dipole moment in that direction. Dipole moment's direction is that way. So here two bonds are there. So dipole moment of this molecule is the resultant of these two bonds. Now let's see another molecule, that is BF3. F. So here fluorine is more electronegative in that way. This fluorine is more electronegative. The dipole moment of this is in this way. That is in that way, right? These two, the resultant is in this direction. So that is cancelled by this opposite one. So the dipole moment is 0. What you have to see is whether there is dipole moment or it is 0. Value doesn't matter for you. Whether the molecule has a dipole moment or more dipole moment compared to other one, or it is 0. In the case of CCl4 dipole moment, in the case of CCl4, in the case of CCl4, look at this CCl4. In this, you see this CCl and the CCl bond, its dipole moment is right at the center, downwards, and upper two bonds are upwards, means in between. This is upwards, and here it is downwards. So these are mutually opposite to each other, equal and opposite to each other. So it gets cancelled. So we say CCl4's dipole moment is 0. CCl4 dipole moment is 0. Here all chlorines are electronegative. On each bond there is a dipole moment. The resultant dipole moment is 0. Now let's say in BeCl2, dipole moment. Here in this direction, here in this direction, they mutually cancel each other. So again dipole moment is 0. You write one question, in which case there is more dipole moment, NH3 or NF3? NH3 or NF3, in which case there is more dipole moment? In which case there is more dipole moment? NH3 or NF3? In NH3 or NF3? That depends upon the structure. NH3 In NS3, this is the shape. This is NH3 shape. Nitrogen here, hydrogen, hydrogen, hydrogen. So here, there is a lone pair. There is a lone pair. There is a lone pair. This is H, H, H. Lone pair, we call it as orbital dipole. Orbital dipole. This is only an orbital. No bond is formed there. This is a covalent bond, covalent bond, covalent bond. Only covalent bonds are directional. So there is nothing. On the top, there is nothing, no direction. So this NS3 has got a pyramidal shape. Now look at this NS3. Nitrogen is more electronegative. So dipole moment is in this direction. And in this case, the dipole moment is in this direction. And in this case, the dipole moment is in this direction. So all directions of dipole moments are towards carbon. So orbital. So the resultant is up. Resultant of these three bonds. The resultant of these three bonds like this. So in this direction, in this direction, in this direction. So their resultant is up. And this orbital dipole moment's direction is also up. So net dipole moment is very high. It gets added up. Orbital dipole moment is towards up. And the resultant of all these three is also in the upward direction. So the net dipole moment, that is very high. Now, what about NF3? This is NF3. Fluorine is yellowish green. This is NF3. In NF3, fluorine is more electronegative. In NF3, fluorine is more electronegative. So dipole moment is in this direction. Dipole moment is in this direction. Dipole moment is in this direction. And orbital dipole moment is always up. So here, in this case, since this is in this direction, this is towards this, this is towards this. So the net dipole moment is towards downwards. Net dipole moment is towards downwards, but the orbital dipole moment is upwards. The net dipole moment, dipole moment is downwards, but the orbital dipole is upwards. So there will be cancellation. When the cancellation takes place, dipole moment becomes very less. So which is having more dipole moment? NH3, not NF3. Looking at that more electronegative fluorine, don't think that NF3 will be having higher dipole moment. No, NH3 will be having higher dipole moment. This is due to its structure. Okay. So you have written the question, which one is having higher dipole moment, NS3 or NF3? Why? Answer, NS3 is having more dipole moment. NS3 is having more dipole moment. This is due to their structure. This is due to its structure. This is due to its structure. And you should draw in this way. N, this is orbital dipole moment H, H, H. Towards this, towards this, towards this. And the orbital dipole moment is towards upwards. What about NF3? N. Orbital dipole moment F, F, F. Towards this, towards this, towards this. So the resultant of these three, is downwards. So I'm showing it downwards. And the orbital, this is the resultant. I'm showing the resultant. The resultant is downwards, but the orbital dipole is upwards. So there comes cancellation. So N of 3 is having lesser dipole moment than NS3, or you can write NS3. You have already written NS3 is having more dipole moment. So polarity of bond, this is due to the difference in the electronegativity values. Polarity of the bond arises. Now how much polarity? 100% ionic bond and 100% covalent bond. That is an ideal situation, and we say there is no bond 100% ionic or 100% covalent. You consider an ionic bond, that is using the elements of first group and 17th group. For example, LiCl. LiCl. LiCl, we expect an ionic bond here. We expect an ionic bond because Li is of first group and Cl is of, I'm writing like this, Cl is of 17th group. Just like our NaCl, LiCl should have been an ionic compound. But here the covalent nature is more. How to explain that covalent nature? Li, Li should change to Li plus and Cl will be changing to Cl minus. But its charge upon radius ratio is very high. Charge upon radius ratio, Li small, charge upon radius ratio is very high. We say its polarizing power. If the charge upon radius ratio is very high, we say polarizing power of this cation is very high. Polarizing power means it is able to polarize the other atom. If the other atom is bigger, then the outermost electrons are not attracted by the nucleus. So this can easily distort that bigger atom. So distortion is more if this anion is bigger. For example, I minus bigger. The outermost electrons are not very well controlled by the nucleus. So Li plus can distort the electron density, and since its polarizing power is more, it will be pulling the electron density towards this. That means electron density will be higher. Electron density will be higher at the center. If the electron density is higher at the center, means it is a covalent bond. We expected an ionic bond, but due to its polarizing power and its polarizability, we say the term polarizability. So polarizing power of cation and polarizability of anion. Polarizing power of cation and polarizability of the anion. Polarizing power means if it is having high charge upon radius ratio. Charge upon radius ratio should be very high. Then polarizing power is high. It can polarize the other fellow. If the other fellow is bigger, then that polarization is very easy. Extent of polarization will be very high. And what is meant by polarizability? If the size is bigger, that can be easily distorted to negative and positive portion. So what happens? This will be pulling the electron density towards it. At the same time, when it pulls, it will be pushing that nucleus of this to the other side. So here, electron density develops here. So since the electron density is coming to the center, high electron density at the center, a ionic bond will change to a covalent bond. That means Li is a pakka covalent compound. How can we prove that? It is soluble in organic solvents. Covalent compounds are soluble in organic compounds. Li is soluble. So the best covalent bonds among these halides of Li, that is Lii. Lii is more covalent than LiBr, then LiCl, then LiF. This is the decreasing order of covalent character. Decreasing order of covalent character. So polarizing power should be high. Polarizing power of the cation, polarizability of anion, and the extent of polarization decide the covalent character of an ionic bond. Covalent character of an ionic bond. Now let's see AlCl3, MgCl2, and NaCl. Which is the best covalent one? Which is the best? We know that Al3 plus high charge and radius small radius. So Al3 plus, here it is Al3 plus, and here it is Mg2 plus, and here it is Na plus. So which is the best covalent compound in this AlCl3? Because it's high charge upon radius ratio. Radius is small, charge is high. Charge upon radius ratio, if it is high, then we say polarizing power of cation is high. Now, anions are the same, chlorine only. So polarizability in all cases same, but polarizing power of Al3 plus is very high as compared to Mg2 plus and Na plus. So, which is the best covalent? Covalent 1, covalent decreasing order of covalent character is in this way. AlCl3 is the best covalent. So we are trying to find out the covalent nature in ionic bonds. And we said AlCl3 is the best covalent among these three. If you are going to find out this ionic nature in covalent bonds, that was our dipole moment HCl. HCl was covalent. Ionic nature of HCl we found out by talking the electronegativity of fluorine. So there we found out the ionic nature of covalent bond. Here we are finding out the covalent nature of ionic bond. No bond is perfectly ionic or perfectly covalent. So 100% covalent character, 100% of ionic character, that is an ideal situation, and no bond is 100% covalent or 100% ionic. So for cation, we'll be using the term polarizing power. For anion, we'll be using the term polarizability. So what decides the covalent character? What decides the covalent character? Three things. That is polarizing power of cation, polarizability of anion, and the extent of polarization decide the covalent character of an ionic bond. Next, we are moving to VSEPR theory for the shape of molecule. Lewis dot structure does not give the shape of the molecule. So, for the shape of the molecule, we are moving to VSEPR theory. Valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. So there will be a central atom for a molecule, and that central atom's valence electrons are to be considered. valence electron. And one electron from anywhere, central atom will be making a bond with the other atoms surrounding it. So one bond means two electron. One electron will be given by, to make a bond, one electron will be contributed by the central atom and one electron from the other atom. So all the valence electrons will be involved in bonding plus one electron from the surrounding atoms. So write some points on valence shell electron pair repulsion theory. Write down. Number one, the shapes of the molecules depend upon the shapes of the molecules depend upon the number of electron pairs. Number of electron pairs in the valence shell of the central atom. In the valence shell of the central atom. So if there are 5 valence electrons, you have to count all the 5. If there are 6 valence electrons, you have to count all the 6. If there are 7 valence electrons, you have to count all the 7. Number 2, electron pairs surrounding central atom repel each other. Means they stay far away from each other, far apart. Electron pairs surrounding the central atom repel each other. To have minimum repulsion and maximum stability. They stay far apart to have minimum repulsion and maximum stability. And so maximum stability. Electron pairs stay far apart. Electron pairs stay far apart to have minimum repulsion so that they have maximum stability. Lone pair repulsion is greater than lone pair repulsion, which is greater than bone pair repulsion. Lone pair means the electron pairs which do not take part in bond formation. Bond pairs means which are already in the bonding state, that line. Lone pairs we show with dots. Next point. After repulsion, the electron pairs achieve definite positions. Only covalent bonds are directional. The electron pairs achieve definite position around the central atom, giving a permanent geometry to the molecule. Giving a permanent geometry to the molecule. Giving a permanent geometry to the molecule. Now what you have to do? Central atom's valence electrons you have to consider. So what you have to do, suppose oxygen, how many valence electron? 6. H2O, H2O. 6 electrons from oxygen and 1 electron from each hydrogen. So 1 plus 1, 8 electrons. 8 electrons means electron pairs repel each other. So these 8 electrons you should put in pairs. How many pairs? 4 pairs. 4 pairs. These 4 pairs will be standing around this oxygen so that they stay far apart to have minimum repulsion and maximum stability. So around oxygen, 2 bonds are there. 1 bond here, 1 bond here, 1 electron pair here, 1 electron pair here. So they stay far apart. In what way? Arrangement of this way. This way. They stay far apart. Arrangement of electron pairs, that is in tetrahedral way. This is the tetrahedral way. This is the tetrahedral way around this oxygen. But two are not bond pairs. 2 are lone pairs. So don't look at for the direction there. So what is this direction? This is bend. The shape is bent. The shape is bent. 2 lone pairs are there. You should not count the shape of lone pair because lone pairs are not directional. Only covalent bonds are directional. Only covalent bonds are directional. Suppose BeCl2, BeCl2. So for BeCl2, boron, Be, beryllium, 2 electrons. Cl2, that is one electron from one chlorine, other electron from other chlorine. So altogether 4 electrons. 4 electrons means 2 electron pairs. These pairs, 2 electron pairs, they will be repelling each other. They stay far apart. They stay far apart in this direction. That is, the shape is linear. The shape is linear with 180 bond angle. The shape is linear. You can see the shape linear. Thank you.